We tend to think of space as this impossibly huge, complicated place, right? Full of forces we can barely wrap our heads around. But what if I told you that we can unlock some of its biggest, most amazing events, like the phases of the moon and solar eclipses, using stuff you could probably find in your house right now? Today, we're going to solve a major cosmic mystery, not with some supercomputer, but just with a change in perspective.
And here it is, the big puzzle. It's a fantastic question, because it seems so obvious, doesn't it? The moon goes around the Earth about once a month. At some point in that trip, it passes right between us and the sun. So you'd think its shadow should fall on us, creating a solar eclipse every single time. But it doesn't. And that's the mystery we're here to crack.
Okay, so to really get to the bottom of this, we first need to get the basic setup straight. We're dealing with three main players in this cosmic dance: the sun, the Earth, and of course, our moon.
Now, the really cool thing about all this is how predictable it is. I mean, our solar system runs like a giant, beautiful clock. We know exactly how long the Earth takes to go around the sun, and how long the moon takes to go around the Earth. And that clockwork precision is exactly what makes the missing eclipses so strange. If everything is so regular, why isn't this one event happening on schedule? To figure that out, we've got to look at it a different way.
The answer isn't buried in complex math. It's all about perspective. And the best way to change our perspective, it's to build a model. We're going to shrink these giant celestial bodies down to a size we can actually work with, so we can see exactly how they move around each other.
So here's our toolkit. It's so simple, it's brilliant. Picture this with me. A flashlight is our sun, the source of all the light. A big ball is our Earth, and a smaller one, that's the moon. With just these three things, we can start to unlock the secrets of their orbital waltz.
Okay, let's put our model to the test. First up, lunar phases. Imagine you're standing on our big Earth sphere. As we slowly move the little moon sphere around you, the flashlight sun is lighting it up from different angles. From where you're standing, you'd see just a sliver of light, a crescent, then half of it, and then a fully lit full moon. See? It's just a game of light and shadow.
And just like that, our simple little model perfectly explains something we see in the sky every single month. This is huge. It means our model's reliable. We can actually trust it to help us dig into our bigger question about eclipses.
All right, now for the main event. Using our trusty model, let's see what happens when we try to make an eclipse by lining everything up just right.
So when you really boil it down, an eclipse is just about one thing: shadows. A solar eclipse happens when the moon's shadow hits the Earth. A lunar eclipse is when the Earth's shadow covers the moon. The whole trick is getting that shadow to land in exactly the right spot. And our model shows this perfectly. For a solar eclipse, we put our small moon sphere right between the flashlight and the Earth sphere, and boom, its tiny shadow falls on the Earth. For a lunar eclipse, we just swap them. We put the Earth in the middle, and now its much bigger shadow gobbles up the moon. The model makes it crystal clear. Which brings us right back to our original problem. We've just shown that if you line them up, sun, moon, Earth, you get a solar eclipse. And the moon gets into that position every single month during the new moon phase. So what's the deal? Why isn't the shadow hitting its target?
Well, it turns out our model and our thinking is missing one tiny but absolutely crucial detail. A secret ingredient that changes, well, everything.
5 degrees. That's it. That is the entire answer to our cosmic mystery. 5 degrees. So what on earth does that mean? It means the moon's path around the Earth isn't perfectly flat. Imagine the Earth's orbit around the sun is like a perfectly flat tabletop. Well, the moon's orbit is like another smaller tabletop that's tilted up on one side by just 5 degrees. It's a tiny tilt, but over the huge distances of space, it makes all the difference in the world. So now, let's go back to our model and add this new piece of information. Imagine tilting the path of our moon sphere just a little bit. Now, most of the time when it passes between the flashlight and the Earth, its shadow doesn't land on the Earth at all. It zips right over the top, or it skims just underneath. The lineup isn't perfect, the shadow misses, and that is why, for most new moons, the shadow is either too high or too low. An eclipse can only happen during what astronomers call an eclipse season, those 2 special times a year when the moon's tilted path crosses the Earth's flat path at the exact moment the moon is between the sun and Earth. Only then do all 3 line up perfectly. Only then does the shadow hit its mark. So we solved it, and the hero of our story wasn't some giant telescope or a complicated equation. It was a simple model,
a way of seeing and thinking that helped us find that one hidden piece of the puzzle that explained everything.
And this is why modeling, whether you're using a flashlight or a computer simulation, is just so incredibly powerful. It takes something impossibly big, like our solar system, and makes it tangible, something we can hold and play with. It lets us test out different scenarios to see what happens. A model helps us visualize that complex dance of light, shadow, and position. And maybe most importantly, it reveals those hidden variables, the tiny details like a 5-degree tilt that turn out to have massive consequences. It's all about finding the right perspective.
It really makes you wonder, doesn't it? We solved the mystery of the missing eclipses just by tilting our point of view by 5 degrees. It leaves us with a final, fascinating question. What other cosmic patterns, what other great mysteries of the universe are just waiting for us to understand them, if only we could find the right way to look?